This is how to draw a battery. They claim it's real easy, but it doesn't look real easy to me. It looks to me like you need art lessons and some kind of talent. This being physics class and not art class, we are not going to learn how to draw a battery. We are going to learn circuit notation. Circuit notation is the art of drawing batteries and everything else you'll need in a circuit in standard notation so that you can read diagrams of any kind of electronics that you might want to be able to use, build, or fix. Take out your note sheet and fill in the blanks as you learn how to draw common circuit elements and what they're used for. This is a wire. It's got copper on the inside and plastic or rubber insulation on the outside. It's a line. If the wires are supposed to be connected in a junction, that's going to require some splicing, some pliers, and some electrical tape or screw-on wire caps. Make that really clear that those wires are meant to cross. If they're not meant to cross, if they're just happen to be flopping them over on the lab bench, make it clear that they're not meant to cross. The symbol for a battery has to do with what's in the battery. It's stacks of metal plates, zinc and copper suspended in acid or something like that. Long is high voltage, that's plus. Short is low voltage. What you have here is the symbol for two batteries. High, low, that's one cell. High, low, that's the second cell. You've got two AA batteries here, or anything else you like. If you count the number of pairs of long and short lines, you'll be see how many batteries the diagram is telling you to put in that battery case. Please note that conventional current flows from high voltage round the circuit into low voltage. So label that direction carefully on your circuit diagram. What if your circuit is not battery powered? What if it's powered by a generator or a turbine, or is just plugged into the wall, which is powered by the generator with the turbine at the power plant in Zion, Illinois? This is an AC source. See the alternating current, the sine wave? Circle means black plastic box, or in this case, red plastic box. What's in the plastic box? Alternating current. We don't care how at this stage in the year. We care that it plugs in and it works. What do we plug in? Let's take a look. A resistor is a small piece of ceramic with a specific length, width, that is diameter, and material composition so as to have a specific resistance in ohms. A resistor's job is to resist the flow of current, to slow that flow down, to lower the current. Imagine how difficult it would be if you had to run through all these zigs and zags. That's why the symbol of the resistor is what it is. A variable resistor. A variable resistor has a dial that can be turned up or turned down, depending on the amount of resistance you have. There are three conducting points inside a potentiometer, which is fancy for variable resistor. And there's a little dial that you can turn. If you want a little resistance, you dial to the left and you connect to a short piece of metal. If you want twice as much resistance, you turn the dial over here so you have twice as much length in between you and the contact point. As far as you're concerned, this is a dimmer switch. You can turn it up for high resistance and low current, or turn it down for low resistance and high current. You've got potentiometers in the engineering physics lab drawers or in your take-home 2020 kits. There are several types of switches. This one is the one that opens, flip it up, the light is off, and closes, flip it down, metal to metal, the light is on. This kind of switch is a push-button switch. See, you push the metal down, the connection is made, the current flows, the circuit is on, you push it again, spring, the metal pops back up, there's no more connection, and the circuit is off. Now, if you think that the symbol for a light bulb looks a little bit like a resistor in a glass ball, you'd be right. You can draw a light bulb as a resistor in a glass ball. This is an incandescent filament, not an LED. Old-fashioned Thomas Edison. Little bit of metal heats up white hot and glows. Ooh, that's going to have substantial resistance. As far as we're concerned, a light bulb is a resistor in a glass ball. It glows. This is a capacitor. Capacitors store charge. This is unlike a battery, which delivers charge. If a capacitor is the Amazon warehouse that has all the volts you need, you just can't go in there and get it, a battery is your neighborhood Joule, where, yes, it has voltage, but it delivers, or at least Instacart delivers from your neighborhood Joule. This looks a little like a capacitor, but it has a big arrow. This is a diode. A diode is a one-way gate. It lets current flow in one direction only, from high voltage to low voltage. Which direction is that? Well, it's in the direction of the arrow. Check the direction of your battery in the circuit. The diode arrow has to go this way, from high voltage to low voltage, high to low, for the diode to light up. If the diode is facing the wrong way, from low voltage to high voltage, then the LED will be off. The current simply will not flow. If you're hooked up to an AC source, that's going to happen fairly frequently, and the diode can be used as a gateway. An LED is a light-emitting diode. The symbol is simply a diode in a glass ball, and it is much more energy efficient than the Thomas Edison light bulb. LEDs are made to emit light. Incandescent bulbs are made to emit heat. 80% or more of that output is heat, and only 20% of the energy you drain from your battery or take from the wall is used for light output. The price you have to pay for using a much more energy efficient source is that you have to remember to plug in the diode the correct way. Long end, high voltage; short end, low voltage. There's your LED, and there is which end is which. Engineering is going to be using a lot of LEDs. CP and Honors Physics, this is a fascinating bit of theory that you will get into when you start building things in other classes. If you think this symbol looks like a coil of wire, you're right. This is an inductor. An inductor is a coil of wire. It can be a coil of wire around a straight core. It can be a coil of wire around a circular core. This is a solenoid. This is a toroid. Interesting side, this is a toroid. This is a torus. It's a necklace made out of strips of wire coiled together into a collar, or in the case of this modern variant, a Torrus, made by a computer programmer who can only think in matrices and rectangles. Those of you who are studying Shir HaShirim with Rabbi Kensky will note that some idiots translate Pasuk Yud Aleph as Toreza Havna Aselach. We will add doves of gold, im nekudot hakasev, with periods of silver. Okay, I don't know about you, but I'm skipping that booth in the art and jewelry show. Who wears gold doves? What is you going as the Birdman or something? No, look at the word, Tor. This is Greek, Torrus. Shlomo buys his jewelry from the Greek islands because they have all the good art and design people coming out of the slave system in Athens. Nikudot are pendants. Shlomo is offering Shulamit in Shir HaShirim a gold Torus with silver pendants if only she will forsake her own true love, the shepherd boy, and go for the material comforts he can provide, just as the real world woos us, saying, we will make you rich and comfortable if only you will forget your spiritual life. The point of Shir HaShirim is that Shulamit in the end says, thanks, you can keep your gems. I'm going to be free and do my own thing with my first true love, much like my spirit is going to be free and seek spirituality, despite the fact that you have Tauruses and we just have Shabbos dinner. But I digress. We'll learn when we do motors and electromagnetism that wire coiled into a coil so that it has to spiral up and down is really good at resisting change. Not resisting current. Current is fine, it's copper wire. But changes in current will find a huge backsurge that resists the change. An inductor prevents sudden increases or decreases in current. Instead of you pulling the plug and seeing sparks fly because, you've got a strong electric field, like how strong your appliance was just on, in that tiny little gap between you and the wall, sparking, setting paper or possibly paint or possibly the wall on fire. Instead, we flip the switch, we send the current through the inductor, and instead of going on, off, spark, it goes on, off, without setting anything on fire. More of the story, use the switch or the button, don't just yank the cord out of the wall. If this looks like two inductors, one next to the other, that's exactly what it is. They could be two coils, one next to the other, each coiled around a common core, or better still, save space, coil the outside one out of the inside one. This is a transformer. It's more than meets the eye, but it's not a robot in disguise. It's a way to step up low voltage to high voltage, or step down high voltage to low voltage, all without violating conservation of energy. If we can get as far as the operation of a transformer in our notes, we will have learned everything a first-year physics student needs to learn about electromagnetism. Some years are like that. Some years we get as far as here and then call it Physics Expo and graduation. These are some different symbols for the ground. This is an earth ground, just like it sounds. It's buried in the earth. And this is a chassis, even though it looks like it's written chassis. You can clamp your circuit to a lead pipe, which is made of metal, which is connected to the pipes in the ground, or you can bury a grid in the ground yourself and run the wires for it directly. We know from our study of static electricity that excess static discharges to the ground. It wants to go to the ground. Make a nice path directly to the ground, a nice copper wire reserved for that purpose, so that it can go to the ground without electrocuting you or setting your house on fire along the way. The third prong is the grounding prong. Ladies and gentlemen, if you are trying to plug a 3-prong outlet into a 2-prong outlet, do not cut off the grounding prong so that this will fit. The grounding prong is there to keep you safe. It provides a low voltage of 0 volts, and that reduces the risk of electrocution by 50%. If your plug is not polarized, if the two ends are the same size, then the current could go this way and the current could go that way, and either way your incandescent bulbs will flash and the appliance will run. If you have a polarized plug where one end is bigger and one end is smaller, the bigger end is the high voltage. You have diodes that will only allow the current to run one way. And if you try to plug it in backwards, A, it will not work, and B, it will not work because the plug will not fit. If you have a grounding prong, it is because the manufacturers of the appliance would like you to come back and buy more things from their company. Dead electrocuted customers do not come back for repeat purchases. They have put in this third prong to keep you safe and not dead. Take a leaf from their playbook and use it. If something goes wrong and you touch the high voltage end of the wire by mistake, what do you mean something goes wrong? Well, if this insulation is frayed and you can see the copper bits hanging out of it, don't plug it in. And if it is plugged in, turn it off for the love of God and don't touch it. 120 volts out of that wall. Look at your Ohm's Law worksheet. You are going to be hurt. However, if you touch the low voltage prong and low voltage has been grounded to 0 volts, you will get an unpleasant surprise, but you won't actually be hurt. That's cutting the risk of electrocution from 100%, 60 volts here, negative 60 volts here, both of them well over the maximum of 32 volts you found on your worksheet, to 50%. I will gladly take a 50% chance of being less dead any day of the week. I also wear my mask in times of pandemic. If you really need to plug something in and you only have a 2-prong outlet available, you can get a 3-prong to 2-prong converter for the short term, but get an electrician to wire up a GCFI outlet ground fault interrupter. We've got another one of those safety devices we're about to take notes on to make sure that you can plug this in and have it be grounded. Speaking of safety devices, here are the 2 big ones that we talked about in the context of shorts in the system. If your current gets too high, there are many causes of this. One of them is too much high voltage. One of them is not enough resistance. The third one is a connection that wasn't supposed to be there, a connection that is short on resistance, thus resulting in the current being too high. Either way, high currents are hot. This gives us danger of overheating, of melting the nice plastic insulation that was supposed to keep us safe from electrical fires, nasty toxic cancer-causing fumes from melted plastic, and oh yes, the electrical fires. If we don't want that to happen, we're going to need either a fuse or a circuit breaker. A fuse is a tiny little metal filament. It's so thin and fine you could break it if you touched it. That's why it's encased in glass. Glass is not known for its electrical properties. So here we have caps on the end to show where the metal's going to go, metal to metal connection. This carefully tempered metal alloy will melt when it gets too hot. How hot? Look on the side. It says in teeny tiny letters that the screen resolution isn't good enough to read, 2 amps. A current of 2 amps is going to be hot enough to melt the metal in that fuse. We'll call that a blown fuse. Take a look next time your speakers stop working. You'll see the little singed in the middle of the wire. Broken wire means no current, means no overheating, no electrical fires. You are saved. Ladies and gentlemen, the blown fuse is not the problem. The blown fuse is the solution to the problem. The problem was the current being too high. Put that in your notes. I'll say it again, nice and slowly. The problem is the current being too high. That poor little fuse sacrifices itself to save you and your house and your possessions. It takes one for the team and it dies so that the current will shut off and so that you may live. The blown fuse is the solution. To fix the problem, there are 3 steps. Write this down. Step number 1, shut off the current. Turn it off. The current was too high. It was overheating, damaging the equipment, and risking fire. Step 2, fix the problem. We said there were 3 causes. Is the voltage too high? Did you take a hammer and try to bang the plug into a place where it manifestly did not fit? If so, you're an idiot. Don't. 2, was the resistance too low? If necessary, take screwdriver, take pliers, take chainsaw, take the equipment to bits and fix the resistance. If this does not seem practical to you, we are about to start learning about circuits where there will be a much, much simpler way to lower the resistance or raise the resistance without having to snip the wires in half to make them shorter or bang on them with said sledgehammer to make them thinner. Once you've fixed the problem and you have raised the resistance to lower the current, you can't fix a broken fuse. You have to replace it. You have to go down to the basement, open up the toolbox, get the little box of fuses, take one out, and put one in the appliance. If you're out of fuses, you will have to make a Best Buy run or buy a pack online and replace the fuse. As you can see, this is not a very cost-effective way to run a business. Ladies and gentlemen, fuses are only used in small appliances, given that you can't fix them and you have to throw them out every time there's an electrical error. If every time the power goes out in your house, you have to go downstairs where there's a big wooden crate and you pry off the lid and you take out something roughly the size of a can of Coke that is horrible and corroded and looks like the ooze container from Teenage Mutant Ninja Turtles 2, The Secret of the Ooze. It's so covered with cobwebs you can't even see that what's in here might be glass. you open a door in the wall, you take out something even older and grodier and still the size of a can of Coke, throw it away, and put the newer one in, then you have a fuse box in your basement. Post it in the YouTube comments if you do. We are up to 4 students in our school in the past 20 years who have had such a box. Usually they're associated with houses in Peterson Park that were built in the 30s but did not have their electrical systems redone in the 50s and 60s, the way houses further north and closer to the lake tend to have done. If instead, every time there's a problem, you go downstairs, you open a small gray panel on the wall, and you flip a switch, ladies and gentlemen, that's not a fuse box. Don't call it a fuse box. That there is a circuit breaker. Different technology, different symbol. Write it down. A circuit breaker is a heat-sensitive switch. It flips the switch off if too much current is flowing, and similarly you can fix the problem and then flip the switch on again. Inside a circuit breaker is a double-sided metal strip, typically one side a copper alloy, one side an aluminum alloy. The point is that each alloy has a different melting point, and when current, let's say 15 amps or 20 amps, which are the different settings on my circuit breaker, flows through it, let's say 16 amps on 15 amp circuit, one of those metals is going to start to lose its integrity and melt. And as it melts, it's going to kind of pull the other one along with it because they are welded together. And as you can see, the metal strip bends and shuts off the circuit. If you want to do this really, really quickly, you can have the metal strip holding a spring in place. So the instant it goes, the spring goes boom and shoots that connection several millimeters across the box. So there's no possible way the metal can be connected and no current will flow, thus not setting your house on fire. All right. So you plug in the dishwasher, the microwave, both ovens, the heat, the fan, the strip lighting in the bathroom because you're taking a shower, and air conditioners all over the house. Friday afternoon, everything's going. Throw in the laundry, washer, dryer, 3, 2, 1. Everything goes dark. So you run down to the basement, you swear, you open the fuse box. And by fuse box, I mean circuit breaker. Get in the habit. You open the circuit breaker, you flip the switch. What will happen?
Things will go on, but then they'll go right back off because they're all still plugged in and
Oh,
working. And it'll happen
it's
again,
just
again,
gonna
again,
happen
again.
again. And you're gonna flip the switch. 3, 2, 1, boom. Flip the switch. 3, 2, 1, boom. I'm embarrassed to say how many fuses I went through in my first set of speakers for my old apartment before I realized that the problem was not the fuse. The problem was not the circuit breaker. The problem was the current being too high. Again, write the 3 steps down, one at a time. Step 1 is to shut off the current. The circuit breaker did that. The current is off. Now fix the problem. Hypothesize if you have every appliance in the house running and all the air conditioners in all of Deerfield. What might the problem be?
The number of things plugged in. Unplug that thing that you don't need plugged in, and then possibly it will work.
Okay.
Unplug more than just one thing.
Once you have fixed the problem, and unplugged something is an excellent hypothesis. When we do circuits, we'll find 2 different ways that could work. Moral of the story, when in doubt, unplug something. And then you don't need to replace the fuse. Then you can reset the circuit breaker. After you have unplugged several appliances, then go downstairs and flip the switch, and then not only will your house not catch fire, you will also be able to run your electrical system. Fuses, ladies and gentlemen, are used in small appliances. Circuit breakers are used in large appliances and buildings because they can be reset. Now, wouldn't it be nice to know if your current was too high ahead of time before you blew a fuse? Yes, it would. And the devices we're going to be using in lab, starting approximately in our next class, are voltmeters, ammeters, and ohm meters. We have all 3 conveniently in one little black and yellow box that we'll call a multimeter. A voltmeter measures volts, an ammeter measures amperes, which is to say current. Both of those you plug into a circuit in different ways, for which you'll be properly trained in class and using YouTube videos. Ohm meters measure resistance in ohms, and you do that not plugged into the circuit. Alternatively, you could use the resistor color code that's painted on the side of the resistor. Why? Because numbers can scratch off. One scratch on an 8 makes it look like a 3, and then aren't you sorry you plugged it in? A color is still a color, even if half of it is rubbed away, to tell you what the resistance is on this resistor, so that you don't have to measure it every time. This is a 4-band code. Green is 5. It's in rainbow order. You get used to it. Blue is the next color after green. That would be 6. Next band is the power of 10. Yellow is 4. That's 10 to the 4th. That's 5, 6 times 10 to the 4th. That's 5, 6 with 4 zeros after it. That's 560,000. Thus 560 kilo ohms. The 4th band is the tolerance, or as we say in high school science class, the percent error. Brown, that's fantastically good. Brown is 1, that is 1%. I'm used to resistors with gold, 5%, or silver, 10%. By the way, you always start with the one that isn't gold or silver, the one typically that's closest to the edge. This concludes our intro to circuit notation. We now should be able to draw the circuits no matter how bad of an artist we are, and can get on to building some of it.